In this video, we're going to look at objects in free fall. And this all started with a guy back in the 16th century called Galileo, and he formulated a bunch of laws that govern the motion of objects in free fall, as well as many other things that he contributed to various different areas of science. Galileo found that freely falling objects are any objects that are just falling under the influence of gravity alone. And it doesn't depend on the object's original motion, whether it's going up, down, left, or right. As long as gravity is the only force acting on it, then it is considered to be in free fall. And all objects fall toward the Earth's surface, and they fall with the same constant acceleration. And we call this acceleration baby g. We use a little g to signify the acceleration due to gravity. And this is constant for everywhere on the Earth's surface. Baby g has a value of 9.8 meters per second squared, or 32.23 feet per second squared. And if we need to use a rough estimate, we can use 10 at times, but typically we are going to use this 9.8. And it's always directed downward toward the center of the Earth, because that's where the Earth's gravity is pulling from the center. We consider all the mass to be gathered at the center. And we're going to ignore air resistance for the most part, because it is fairly negligible and small compared to the acceleration due to gravity. And even though it does technically change as we get farther away from the Earth's surface, as long as our vertical distance from the Earth's surface is minimal, then we will say that the acceleration is constant throughout. So let's look at an object that is just dropped in free space, and it starts to fall. So initially the velocity is 0. So we're holding an object out and we let go. So it has initial velocity of 0, and then it starts to move towards the surface of the Earth. And we typically say that up is positive, and that's just our normal convention. And so if that's the case, then our velocity that starts becomes negative. It goes from 0 to a negative velocity. And we can use the kinematic equations to solve for any displacement or time. And typically when we do the displacement, since we're talking vertical displacement, we will use y instead of x. And we know our acceleration is always going to be constant, and that's just a value of negative 9.8 meters per second squared, and it's negative because we're saying up is positive. Another situation would be an object that's in free fall, but that is thrown downward. So if you think about dribbling a basketball, you apply some type of force to the ball as it goes down. So we have the force that you apply as well as the force of gravity pulling on it. So it's going to have an initial velocity that is downward, or initial velocity that's negative, and it's also going to have this acceleration that's downward, which is also negative. So it is speeding up just like the situation before, but it starts with an initial velocity that is not equal to 0. A third situation, and one that we'll deal with a lot more often, is one that is thrown vertically upward. So it is initially thrown upward with a velocity that is positive, so we have a positive initial velocity, but then because its velocity is positive and the acceleration is negative because it's going down, this will start to slow down until it reaches its highest point, which is where the velocity is equal to 0, because in order to go up and then come back down, it has to stop at some point. And then this comes straight back down, speeding up as it goes. A few key points to remember here is that at the maximum height, we do have an instantaneous velocity of 0. The acceleration is always and forever constant of a negative 9.8. And as long as we're ignoring air resistance, we are going to see some symmetries come out. In a situation that has symmetry, meaning that where we release the object and catch the object at the same position, we'll notice that there are a few things that are equal. One of the main things is that the time that it takes to go up is equal to the time that it takes to come back down. So the time that the ball leaves your hand until it reaches the max height is the same as falling from the max height back to the original launching position. Also, the velocity that you start with is going to be the opposite of the final velocity. So if we have an initial upward velocity of, say, 10 meters per second, as the object comes back to that original position, it will have a velocity of a negative 10 meters per second. If we have a situation that the motion is not symmetrical, then we need to break the motion into various parts where we have symmetry, or just break it down so we can look at different situations. Typically meaning break it down from going up and then the trip down as two separate instances and treat those instances separately. Let's look at a non-symmetrical example. And here we have someone standing on top of a building that is 50 meters above the surface of the ground, and they're throwing a ball up, at least from where the ball is being released is 50 meters above the ground. And as it goes up, it reaches its max height up here at some point, and then will travel back down. But instead of hitting at the building, it's going to continue going all the way down to the surface level. So this is going up and down, but it's not symmetrical in that we have a starting point up here. And so we want to break this into two parts, the part of traveling up and then the part of traveling down. And so if we look at the part traveling up, we see that the initial velocity is 20 meters per second, and we know the velocity when we reach the top is going to be 0, because when it reaches its max height, its instantaneous velocity is 0. And so we can find other information such as the maximum height and the time based on our kinematic equations that we looked at in the one-dimensional video earlier. So we can use that information to find how high is this ball going to go and how long is it going to take. Well, from that we can look at this situation as basically this is just a ball being dropped from this height of 50 plus the 20.4 meters it travels up to reach its max height. So this red portion here is simply just dropping a ball from 70.4 meters. And so we can find the final velocity from our kinematic equations, knowing the initial velocity is 0. And remember, the acceleration through all of this is equal to a negative g. The acceleration is down the entire time. And so from that information, we can find any piece that we need to know. Let's look at another example with this same situation in that we're 50 meters above the surface, and the ball is launched up with initial velocity of 10 meters per second. And so this ball is going to travel up, and then it's going to travel back down. And let's say we want to find three things. First, we want to find how high does it go from the surface of the earth, so from the very bottom. And then we want to know how long does it take for the entire trip from when it's released until when it falls, and how fast is it traveling before it hits the ground. So first let's talk about how high is this going to travel. So let's break this up into when it initially leaves until its max height. So let's look at our initial conditions and our final conditions. Well, initially we have a velocity that is positive, and it's 10 meters per second. We also have an acceleration that is a negative 9.8 meters per second squared. And that is the same initially, and in our final situation we also have a negative 9.8 meters per second squared. Well, what else do we know? We know that the final velocity is going to be 0. It's going to be 0 because we're getting to our max height. So we need a kinematic equation that relates velocity, acceleration, and then since we want how high, displacement. And so that kinematic equation is the final velocity squared equals the initial velocity squared plus 2a. And in the last section we used delta x, but that was for a lateral distance. So let's use a vertical distance of delta y, or a vertical displacement. And so simplifying and solving for our variable here, we get this is equal to 0, move that over to the other side, and we get delta y is equal to a negative of the initial velocity squared over 2 times the acceleration. So our delta y is equal to a negative 100 meters squared per second squared, and the units are squared because we're squaring the quantity, so the units get squared as well. And this is over 2 times a negative 9.8 meters per second squared. And if you notice, the per second squared cancel, and a meter cancels with one of the meters, so we're just left with meters, which gives us the correct units. And this gives us 5.1 meters. So this tells us how high above the surface of the building, but we want to know how high above the surface from the ground, and so that will be 55.1 meters, and that is the height that we get above the surface of the ground. Now let's look at how long it's going to take. And so let's look at this first piece of just reaching our max height. And to find the time using the same initial conditions, we want to look at our acceleration formula, where our acceleration is equal to the change in velocity over the change in time. And so that tells us that the time that elapses is going to be the change in velocity divided by the acceleration. Well, what is our change in velocity? We go from 10 meters per second to 0, so that's a negative 10 meters per second divided by a negative 9.8 meters per second squared, and so that gives us about 1.02 seconds. And double check the units, the meters cancel per second squared, we end up getting seconds, and so that is correct. Now, that is only the time to the max height. Alright, so this is only the time that it takes to travel up. Well, it still has to go from the maximum height all the way down to the surface of the earth. So let's look at that situation separately. And so in that situation, we have basically just an object being dropped from a height of 55.1 meters. So we know our displacement is going to be 55.1 meters. We know our initial velocity is going to equal 0 because we're up at the top and we're stopped initially, and then we're going to have some final velocity that we don't know, but we do want to find eventually, and we have an acceleration that's a negative 9.8 meters per second squared. So we need a kinematic equation that uses velocity, displacement, acceleration, and the unknown that we're trying to find, time. That kinematic equation is our displacement is equal to the initial velocity times time plus half the acceleration times time squared. And so we know our initial velocity is 0, so that piece can go away, and we want to solve for time here, and so we get our time is equal to the square root of 2 delta y over a. Now you may be asking, shouldn't there be a plus or minus here? And algebraically speaking, you are correct. We should have a plus or minus when we're solving for t here, but here's the thing, can time be negative? No, it can't, so we throw that out and we only keep the principal square root, or the positive root. And so when we plug in our numbers here, we get the time is equal to the square root of 2 times 55.1 meters divided by 9.8 meters per second squared, and we get about 3.35 seconds. Now remember, this is just our trip from the top down to the surface, so we have to add the two together to get a total time of 4.3 4.37 seconds. So from the time the ball leaves your hand, going to the max height and all the way down to the surface, it'll take 4.37 seconds. Finally, let's find how fast. And so to find how fast, we still want to just look at that second situation of traveling down, in that we have a displacement of 55.1 meters. We have an acceleration of negative g. We can use our time, or we can look at our initial velocity is 0, and we want to find what is our final velocity. So we go back to the kinematic equation where the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Now to solve for the final velocity here, we do want to take a square root of this entire quantity of the velocity, the initial velocity squared plus 2 times the acceleration times delta y. And this is where we need to be careful of our signs here. And I will point out that I made one little mistake, or at least I didn't keep my conventions consistent when I stated the given information in this part. Now, we're still assuming that up is positive. And so if up is positive, we do have a negative acceleration for g, and we expect our final velocity to be negative. So that's why we're going to have a negative sign out here. But this is what's important. What is our change in y? Well, if up is positive, we are going down, so our displacement is also negative. Okay, and the reason this is important, because when we go through here and plug in numbers, we see that that's 0, and we want the negative square root of 2 times a negative 9.8 meters per second squared times a negative 55.1. And if we don't have that negative 55.1, then we end up having a negative inside of a radical, and that's a non-real solution. And some might say, oh, we'll just ignore it and keep it positive. Well, sometimes having those non-real solutions alerts you to the fact that maybe you did something incorrectly, or you need to check your coordinate system or your frame of reference. So we need to make sure that we get a real number, so that means we have to have a positive number inside of the radical, or a positive radicand. And so when our displacement is negative, which it is because we're going down, these two negatives would cancel, and we end up getting a positive quantity of about 32.9 meters per second. And so that is our final velocity right before it hits. And remember, it is negative because it's going down.